All right, so this will be a couple examples from your work from this week, the multiple angle and product of sum identities. You have a couple problems on that problem sheet. This goes along with them. I have a couple examples from that sheet specifically, and then one's very similar to it. So let's talk about a little note first. So if you remember when we first started learning about trig, this is how we would determine our sine, cosine, tangent, and then in turn also our cosecant, secant, and cotangent. So remember that once we start working with the unit circle, we kind of forgot about this r, because in a unit circle, your r is 1. So you don't really need to write it. We knew it was always like y or 1 over y. But now we're not really in like a unit circle. We're just graphing our degrees and our angles here. So that's why we need this y over r. So we can't forget that because we had worked with a unit circle so long, this was a 1. But when we initially learned these, we have r's here. Okay, so maybe you want to take a second and write these down if you don't have them in your notes or you don't see them. These are going to help you with especially that first group of problems. So let's look at an example of that first group. So let's break down the information that's given to us. They are giving you, for instance, this was number 2. This was the first one that was given. They're giving you a tangent value. They're also giving you an interval. So this interval, it's not necessarily telling us that we have like more work to do, but it's telling us what quadrant we're working in. So this is the third quadrant. If you look at number 4, it's in radians, but they tell you between 3 pi over 2 and 2 pi. That's your fourth quadrant. So that's what that is. It's just an interval. It's kind of like what angle measures what quadrant are we looking in. We're looking in quadrant 3. So going back to those notes from either a while ago or from the previous slide, we know that our tangent is y over x. So that tells us that if it's in quadrant 3 and our tangent is our y over our x, that means they're both negative. Our y is how far down it's going, so -8, and our x is how far to the left it went, so -15. So the only thing we're missing now is r, and we can find that fairly easily just by doing the Pythagorean theorem. So I kind of like shaded in this little triangle here so you can see that I wrote it over here as well. You can find that missing r value. So that's good because once you find that, it's pretty much smooth sailing from there. So we found our r value, which is 17. Remember, that's just a distance. It's your radius. It's not going to have a positive or negative value. It's just a length. So that is your r, 17. I always like to kind of organize what I have. So my given information right now is that my x was -15, my y was -8, and my r is 17. So once I find that, I can just determine like my good old-fashioned sine and cosine by plugging them in. And my cosine's plugged in. And we can use these 3 values now, our tangent, our sine, and our cosine. We can use them with our double angle identities to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So once I have those values, now you can see down here, I have solved for the double angles. So pause it if you need to. This one's pretty straightforward. You just go back to your given information and plug it in where needed. You're using your identities, using your algebra skills, and reducing it as much as you can. Don't go nuts. You can see these types of fractions are going to be a little wild. Don't go nuts with trying to reduce them. These are good. So this type of problem is very similar to numbers. Well, this is number 2 and then 4 and 6. So that should guide you with those other problems. Now let's look at the next group of problems. All right, so this is not one of the problems from your page, but it's really similar to numbers 10, 13, and 14. So now we have equations, so we have trigonometric equations, and we kind of want to simplify it as much as possible. So a good idea to think about now that we have these other properties that either help us with degrees or double angles, always try to get everything down into just like the power of 1 and 1 theta on the inside. So I see that on the left-hand side of my equation here, I have sine of 2 theta. That's kind of a good indication that I'm going to be using a double angle formula. This is a double angle. We want to break it down. Once you do that, this is just like your work from, weeks 1 and 2. So just do what you can to solve. So I divided by sine on both sides, which leaves us as a 1, divided by 2. And then now it's that same idea from weeks 1 and 2 where I need to look at my unit circle and I need to figure out what degree or what angle measure will give me 1/2 as a cosine. So look at your unit circle, you're looking for which measures will give you 1/2 as a cosine. And it turns out that it's either going to be 60 degrees and 300, or you could also write it in radians, which is pi over 3 and 5 pi over 3. All right, so on to the last group. So these are similar. This is number 29, and it's similar to all of the problems after number 29. Now the directions basically just say find the exact value, and then they give you different sine and cosine and trig values. So when you're looking at this, our sine of 67.5, you have to remember, or you have to reference your unit circle. 67.5 is not one of the measures on our unit circle, but it is half of 135, and that is. So if you can notice that if you double this, will you end up with one that's on your unit circle? Then you can use what's called the half angle identities. 67.5 is half of 135. When I rewrite it, now I can see that my actual theta, or the u, I forget what your other notes use, is 135. It's 135 over 2. It's equivalent. I didn't change any value. I just changed the way it was written. This is the half angle identity for sine. Plug in my cosine, the theta into my cosine. Do a little bit of algebra here. So this one's a little weird because it does have a square root inside of a square root. And as you can see, as I go down my work here, let me go a little bit bigger. So as I go through my work, my answer does include a radical in a radical, and that's okay. So I plug in negative root 2 over 2. I got that from my unit circle for the cosine of 135. I did a little side work so I can combine them into one fraction. So there we go. Now we know that it's really like times 1/2, so it's another 2 in the denominator. And the only thing you could really do further from here is you can square root the top and square root the bottom, and your denominator just reduces to just 2. Your top just stays the square root of 2 plus the square root of 2. It's a little messy, but this is a perfect answer. It's a valid solution. Don't think it's wrong if you end up with a radical and a radical, and you are good to go.